Hello again, grade 10s. So in this video, we're going to go through how to balance a chemical equation as well as include phases of matter within your equation and make sure that you have zeroed out the charges of each component when it comes to balancing. So this is just a revision slide on exactly the stuff that we learned last year regarding the grocery list method. I hope you guys remember that. Remember, when we get given a chemical equation, what we do is we list on the reactant and the product side the metals and non-metals, the hydrogen and the oxygen, in that order on both sides. The number of atoms for every element on each side needs to be listed as well as balanced. You balance the chemical formulas by changing the coefficients and not the subscript. I don't want to see that ever. If I ever see that, there's a line through your entire chemical equation. Once one element is balanced, proceed to the next until the equation complies with the law of conservation of mass. Remember, equal mass and atoms on either side, reactant and product. So what you're going to do now, before you carry on to the next section, so please pause the video, is you are going to balance page 1 equation. I think there's like 3 or 4 equations there. I don't want you to write out the word equation. I just want you to balance using coefficients. Once you have done that of page 1 of your notes, you can carry on to the next part of the video. So just pause now, do that quickly, and then stop, click play again. Okay, so we spoke about this in lesson 1, phase states or phases of matter. Now let's go and look at phase notation again. So I'm going to keep repeating this until you guys know this off by heart, because this is tricky. This is really, really tricky. It might look easy now, but later on it gets a bit more complicated. So the physical state of the materials in the reaction needs to be noted in italics at the bottom next to the actual compound. So S is solid, L is liquid, G is gas in lowercase. Aqueous means dissolved in water, and then a downward arrow is your precipitate or your solid. Upward arrow is going to be, once again, means that gas is formed. And then as soon as you see that delta sign, what is that? That means that it must be heated for the reaction to take place. The phase notations are written in the lower right of each formula. Okay, clues to phase notations are often given in equations written in words. So you will see, I think it's on page 5 in your book, you will see that there are 14 written descriptions of equations, and in those descriptions, so you can have a look at them now quickly while I'm speaking. You will see that it actually says there liquid or gaseous or solid. It actually tells you what it is. Remember, if it's an elemental metal, it is going to be a solid. If it is a diatomic molecule, the chances are it is going to be a gas, but we'll get into that a little bit later on in the video. So once again, grade 10s, I'm sorry if I'm repeating myself, but here are another 3 steps in your approach of balancing. So these 3 steps, I want you guys to, besides the grocery method, I want you to be cognizant of this. So write these in, and we do this later on. So once you have the actual chemical name, so say for example, it's now a word equation, it's not a chemical equation, this is what you will do. You will identify reactants and products in your word equation. All right. Then you will convert them into the chemical names. And sometimes naming and writing formula is a bit tricky. We get into that in lesson 3. And you write in the phase state symbols. Then you balance. So you don't just balance straight away. When you get given that word equation, you convert to chemical equation. All right. You include the phase, and then you balance. There needs to be a protocol. You guys need to have a method. You can't just be haphazard all over the place. So remember, in physics, there's a method on how you target the problem. So with waves and with EM spectrum, we looked at the problem. We identified, okay, this is a formula I need to use. This is the stuff that's missing. This is what I need to convert. Here I need to substitute. Here I need to write the answer in units. It's the same thing here, guys. There needs to be a method. So please please just have a look at this, write this down as what to do when you get given the word equation. What to do when you get given the word equation. Once again, I am using an example to just identify the different components of the actual chemical equation. So here we have zinc, which is a transition metal, and can you see it's solid? Then you have hydrochloric acid. Again, it's aqueous form. So acids are going to be in aqueous form. We formulate them, we make them in aqueous form. Okay, you're not going to find them in solid form. So it's always going to be aqueous. So you can make a note there, acids are aqueous. Okay, then you see there's a coefficient. What is a coefficient again? Grade 10. The coefficient is the number of molecules, So 1 molecule of zinc, okay, this is the mole ratio, yeah, or the ratio of mass. It's 1 to 2 with the reactions. So 1 molecule of zinc, okay, with 2 molecules of hydrochloric acid is going to form in the direction, it's going to form the reaction, okay, zinc chloride, right, in aqueous form, so therefore that's not a precipitate reaction, and because chlorides are actually quite soluble, they're very soluble. So zinc chloride plus hydrogen gas. How do we know that's hydrogen gas? Because hydrogen is one of our diatomic molecules. So this is a single displacement reaction. Below there's another example of a phase state, and let's just hope and see I can read my own examples here. It says write the balanced chemical equation that represents the combustion of propane. So now this is an example of what you could get in an exam or test. So you would have to know the chemical formula for propane, and you guys don't know that, so we've given it to you over there. And it's what is combustion? Combustion is the addition of oxygen, okay? And what you can see over here is that we get carbon dioxide and we get water, okay, in liquid form. It's actually quite rare because that if it's very, very hot, it's going to be in gaseous form, okay? So here they've given a solution where you write the unbalanced equation, you leave oxygen until the end, and you balance all the other atoms. So make sure everything, you obey the conservation of mass, and then you double check to make sure that there are equal numbers of each type of atom on both sides of the equation. This slide shows the important take-home message for this video. We revised our balancing of equation with a grocery list, as well as how we convert from word equation. What else did we do? We added the phase states. Now, this is new material for you guys, and this is what I want you, this is going to be the highlight of this lesson, and I want you to take it away. How do we determine the phases of elements or compounds in a chemical reaction if it's not, there's no description? How do we do this? Okay, there's 2 ways to do this, and it's the reaction type and the solubility rule. So what is solubility? It's got to do with whether a compound is going to be soluble, so it's going to dissolve completely in the solvent, which most of the time is water, or it's insoluble, so that means that the solute cannot dissociate or break down in the solvent, which is mostly water. The solubility rules looks at ionic compounds, looks at different types of salts, and looks at different types of polyatomic ions, which you're going to learn later on, and explains how when these salts and ions and metals are combined, okay, is it going to produce a substance that is going to be soluble or insoluble within a solvent? That is what solubility rules are. So if you go to your data sheet that I uploaded under files, you have that data sheet with you, you will see that the solubility rules are outlined there. So there's different groups of these salts or polyatomic ions, okay, that have specific rules and exceptions. So these sort of salts would be like your halides. So those are your iodines, your bromides, your let's see, your oxides, your hydroxides. There's also carbonates. Carbonates is carbon and oxygen. There's also chlorates, okay, or chlorides, which are your with chlorine. Chlorine is involved over there, okay? So there's many different types of salts and specific chemical species that work in their own way. They work as their own individual units, okay? And most of these have a specific charge. And combined with another element, that charge is neutralized. So what I want you to do, I think if we look at the top of the page, the top of the slide of here, have examples of solubility. So that's what I want you to take home now, solubility. Then we'll get to the salts. Then we'll get to the different chemical species. Because we were not meant to teach you guys this now. We were only supposed to teach us in precipitation. But I think it's important for you to know the solubility rules because it's going to really, really help you to predict your phase state based on these solubility rules, because you can actually predict your product based on these rules. It's actually super cool. So at the top of the slide, you will see there the salt is added in the water, the solute is the water, the solvent is, the solute is the salt, the solvent is the water, and this makes up a solution. And the salt is soluble as it is dissolved. Versus flour, if you think about flour here, okay, this is added to water. The flour has not dissolved, so it's insoluble. If you need any help, use this analogy. Come back to this analogy if you need any help with this, okay? Before we look at our solubility rules, which are super important when we are trying to predict our phase states, okay? And grade 10s, I might be going a little bit ahead here and might be teaching you stuff that you shouldn't know at this point, but I think it's going to really help you later on. Like, you're going to be ahead of the game. There are some complex polyatomic ions. And like I said before, these are chemical species that have their own, they behave in their own entity. It's an own entity and it behaves in its own way, okay? And they have a charge. So they are, a lot of the times, they're non-metal elements that have bonded, so it's covalent compounds, okay, or ions, and they have an overarching charge, okay? And these species bond to metals as well as non-metals. So you need to know these off by heart. And this is on page 2, so I want you to write in all of these. And you'll see the charge for each one is being put in there. So if I take the carbonate and let's use sodium carbonate for an example. A carbonate ion has got an overarching charge of 2 negative, -2. Okay? Right. What does that mean? It's got 2 extra electrons. So it's negatively charged. Therefore, when it bonds to a metal ion, which is positively charged, that metal ion has to have the same charge. How do we get the same charge? Think about sodium. Sodium is in your first group of metals, okay? It has got a +1 charge. Therefore, I'm going to need 2 sodium atoms, okay, to make sure that I stabilize that carbonate. Because if I don't do that, then I'm going to have a chemical species that's going to be negatively charged. Because the negative and the positive are not equal. So 2 sodium atoms with 1 carbonate polyatomic ion. They bond together and they are therefore neutral and stable. So please write these down. You need to know these all off by heart. Okay, they operate in varied ways and very interesting ways, and we will learn all about them during this year as well as next year. This is literally a cut and paste version of your printout from your chemistry data sheet for an exam, and these are your solubility rules. You do not need to learn these off by heart. These will be given to you at every examination where you need them. Solubility rules will be given to you. And they relate to your halides, so your halogen ions or your halogen polyatomic ions, your sulfates, your sulfides, your hydroxides, your carbonates, your phosphates, any polyatomic ion, any salt is going to relate it. So any reaction that results in a salt is when solubility rules apply. So exchange reactions. These are very important for exchange reactions. Where synthesis reactions and decomposition reactions, we can almost predict what's going to happen because we know how our elements behave. We know how our gases behave and our liquids behave. So in those situations, like decomposition needs heat or light or electricity. So because of that, there's going to be, chances are that solid is going to become a liquid, or that liquid is going to become a gas. In synthesis reactions, if a solid is being combined with a gaseous element, chances are you are going to get a solid. Okay, so you can predict those quite easily. But when it comes to exchange reactions, it's a little bit more tricky, and that is where we use our solubility rules. They really, really help you out a lot. So have a look at them. You will see there's some exceptions when it comes to the transition metals. That's why if you look at your reactant side and you're trying to predict what your solid is going to be and what your aqueous product is going to be in a double displacement reaction, have a look at your salts. Okay, like for example, let's look at this. Okay, salts containing group 1 elements are soluble, so they're going to be aqueous. Okay, salts containing a nitrate ion are soluble. Salts containing chlorides or bromides or iodides are soluble, or generally soluble, but there's exceptions there. The exceptions to the rule are the halide salts. So if it's a halide salt with silver, with lead, or with mercury, okay, that's an exception. That's definitely an exception. Then you have so silver chloride, for example, and this is going to be exception. Okay, lead bromide is going to be exception, and mercury chloride. So those are halide salts. Your chlorides, your bromides, your iodides are halide. Halide meaning halogens, because those are in your halogens group. Silver salts are insoluble, meaning they are going to be precipitates. Most sulfate salts are soluble. Okay. Important exceptions to the rule include calcium sulfate. Okay, right? Barium sulfate, which are both within your metal group. Lead sulfate and silver sulfate. Most hydroxide salts are slightly soluble, so hydroxides are very iffy, so I want you to read this very carefully, okay? You need to use your deductive reasoning skills here quite a lot. This takes practice. This doesn't happen overnight, I promise. I'm sorry to burst your bubble. It's not something that's you're going to do this once and be able to do it with every equation, because every equation is different. Hydroxide salts of group 1 elements are soluble. Hydroxide salts of group 2 elements are slightly soluble, so not 100% soluble. And hydroxide salts of transition metals are insoluble, so you're going to get a definite precipitate there. All right. Most sulfides of transition metals are highly insoluble, so you're going to definitely get a solid there. So iron sulfide, okay, zinc sulfide, silver sulfide, okay. Then at the bottom, I think even on your page, I just want you to add there where it speaks about carbonates. I want you to add phosphates in there as well as insoluble, except with group 1 metals and aluminum. So please just add that onto your data sheet because it's going to help you later on with your equations. But grade 10s, I don't want you to stress about this. I don't want you to stay up at night about this. You do get these solubility rules in every assessment, every exam, every test. So this will be your reference point. The practicing of how to read these, that comes later on. And you'll see we're going to have lots and lots of practice of this, and it will become second nature to you. I think I've mentioned a lot of this already in previous slides and previous comments, but we're just going to add on to the whole reaction type, determining your phase of matter for the products in an exchange reaction. If a displacement reaction has taken place, you need to assume that it was taking place in water unless it was stated otherwise. It needs to be in water. Okay, therefore it's aqueous. An acid is always an aqueous phase during single displacement. If a salt was produced, then look up your solubility rule. So AQ for insoluble, for soluble, and S is for insoluble. Because remember, that's your precipitate. That is your solid that is formed. Non-metal oxides are in gaseous forms. Non-metal oxides are in gaseous forms. Diatomic molecules are gaseous, except bromine, which is liquid. Also, don't forget about mercury, which is liquid at room temperature. Okay, a lot of people forget about that, and then when they're busy trying to work out the equation, they'll put then, because mercury is metal, they'll put solid. Believe me or not, it happens. Then water is gaseous in combustion reactions because of the heat, extreme heat. There's an example here that I found, and I've added it to the slide. Please don't worry so much about when they talk about solubility rule 1 or rule 6 or whatever, because we have not written it like that, okay? But you can look up the particular rule that this example is talking about on your data sheet. So here we've got sodium hydroxide with magnesium chloride, both in aqueous solutions, because they are, what are they? They are ionic compounds. Okay, ionic compounds. You got to first predict the products of this reaction using the knowledge of the double replacement reactions, which remember that the cations and the anions are going to switch partners. So before you do anything else, you are going to switch the partners. So you're going to get sodium chloride from this reaction, and you're going to get magnesium hydroxide. Yeah, it's being balanced a bit. Then you consult your solubility rules, because the last thing you're going to do is you're going to add your phases to determine the product. So group 1 cations, group 1 ions, okay, and chlorides are soluble. Okay, so sodium chloride will be soluble in water. So sodium chloride is going to be aqueous. However, rule 6 states that hydroxides are insoluble, and thus magnesium hydroxide will form a precipitate. Remember, it's not rule 6 in your notes. It's just rule 6 for this example, wherever this example has come from. I found this example, and I thought it was a nice way of explaining it for you guys. So, therefore, your resulting equation is going to be sodium hydroxide, which is going to be aqueous. Remember, it's an ionic exchange reaction. Magnesium chloride, ionic exchange reaction, aqueous, is going to form sodium chloride, aqueous, and magnesium hydroxide, which is a solid. So have a look at this. Maybe add this as a little example once you have written down or done a mind map for these particular rules and conditions. You can do it bullet point, you can do it in little boxes, whatever works for you. This is the last example that I found, which was quite nice, and I don't want you to worry too much about. They mentioned something called a net ionic equation. You do not do that now. You only do that when we do precipitates later, and that includes breaking down the ions within your equation. Don't worry about that at all. Here we've got a double replacement or displacement. The two terms are interchangeable. That reduce it to the, and that reduce the, they're asking to complete it and reduce it to the net ionic equation. You are not going to do that here. Yeah, I just want you to concentrate on the actual phases. The phases are important here. According to the solubility rule, there is no precipitate form. So just because no solid is in your equation doesn't mean there's something wrong. There's nothing. It just depends on the reaction type, and it depends on the solubility rules. So the predicted products of this reaction are cobalt sulfate and sodium chloride. From the solubility rule, cobalt sulfate is soluble because it states that sulfates are soluble, and it doesn't relate to cobalt being an exception. Similarly, we find that sodium chloride is soluble based on rules 1, 2, 3. After balancing the resulting equations as follows, can you see there that you first write out your equation, then you look and you write out your reaction, then you predict your products based on what you know about single and double displacement reactions. Then you balance, and the last thing you're going to do is adding your phases. Okay. Don't worry about separating your species in ionic forms. We don't do that later. We'll do that much. We don't do that now. We do that much later. I hope this makes sense, grade 10s. And in the next video, we will be looking at writing formula as well as naming of compounds. Have a great day. We will chat soon.